Uh, so I have recently joined last year. I will talk about the solar radiophysics, which we are doing at Udaipur Solar Observatory of Physical Research Laboratory. I am showing one of the antennas as the front end, which we use to receive radio waves. I'm an astronomical instrument person, so I will talk about instrumentation. Before that, Udaipur Solar Observatory is on a man-made island here inside a man-made lake named Fateh Sagar Lake. Sir, completely tourist place. You all should visit sometime. So here we have two optical telescopes which sees the sun's photosphere and chromosphere. This year also marks 50 years of this observatory. So we will be celebrating 50 years of this observatory next year in Feb as an international conference. However, the radio telescopes are not here, but it is on the mainland where the main office is. So all the radio instruments which we build at Udaipur Solar Observatory, as the name suggests, is to observe the sun. So as we know, sun is a variable star, and anything that happens on the sun has a direct impact on near Earth atmosphere, that is space weather. This plot here shows the solar cycle variation. We have this level near cycle where when it starts, there's like less activity, and when it peaks, there is a lot of activities. You might have heard about last year, May and October event, which was very severe. There were so many auroras seen almost till as low latitude as in Poland in May last year. However, these also have adverse effect because since they send a large amount of plasma material, magnetic field, charged particle towards the Earth, it can affect anything that comes into the path. So this is a kind of a summary plot which says anything that happens on the sun can produce disturbance near the Earth. What is already known is that sun is a magnetic star. So if we have a handle on the magnetism here, we can kind of know the intensity or the what kind of impact these radiation when reaches near Earth can do. So all the solar physicists, we try to predict what's going to happen near the Earth when these kind of, say, emission or these kind of radiation reaches the Earth much before it actually reaches the Earth. So this can end up doing radio blackout or solar radiation storm or geomagnetic storm, which we all are very well aware of. Where does the radio observation come into picture to do all this? So the image you are seeing here is the sun's image from 300 megahertz to all the way from till 17 gigahertz. You can see the brightness temperature of the sun is displayed here. When the frequency is low, you can see there are these big blobs, and when the frequency increases, you can see the sharpness of this image. Basically, the spatial resolution gets better. That comes from resolution is directly proportional to the wavelength. So wavelength decreases, resolution becomes better. However, the radio observations can give us direct a lot of plasma properties. For example, its density, temperature, magnetic field intensity. Those are very crucial, especially very close to the sun, in order to predict the space weather precisely. Radio emission can come from any part of these transients. This is a standard flare CME model, and this is the photosphere. The magenta color here denotes, and these Roman numbers here denotes the kind of radio bursts that can come from the sun. And as we can see, say for example, you have this magnetic field lines, and then you have, when it erupts after the reconnection, we have this moving outwards of the sun, and then we have the shock. So if we can see, some radio bursts can come from the footprint, some radio bursts can come from inside this coronal mass ejection, and some radio bursts can come from the leading edge of this. So basically, if we have radio imaging observation, we can track the property of this eruption at each and every part of the eruption. That is why radio observations are super important. However, we have a demerit, that is our spatial resolution is very poor. That is because of our wavelength. So even if we have a radio telescope, a radio interferometer of the, say, diameter of the Earth, we still would be around 10 to the power 9 times poorer in resolution compared to other, say, optical observations. However, our advantage is when we study the sun in radio wavelength, we can go to the temporal resolution of as low as 10 millisecond. So each of these maps can be made to 10 millisecond time differences. That means anything that is happening on the sun, and if it is happening very quickly, we can map it here. So this is how a solar eruption looks like. It's called coronal mass ejection. And the previous image which I showed here, this might erupt as a CME later and can be seen and mapped like this in radio wavelengths. Another advantage is radio observations gives us access to the solar, that means which we saw the image previously, the heliosphere, because we have some point observations there, as well as ionosphere, because there is another branch of this called scintillation studies that could give us information very nicely much before the eruption reaches the earth, and it can help us predict the space weather phenomena. So now we'll talk about how solar radiophysics started at Udaipur Solar Observatory. So that started much before I joined. The first thing when we start to make a radio observatory is to get the radio frequency interference survey, and that is what was done. We found out, because it's city, so we found out that the spectra is not very clean. You have these bands here and there, but this will be present everywhere because these are kind of universal signals. However, after around say 250 megahertz, we have a very flat band, and that's how we started. And the first instrument which USO guys had is something called Callisto. Callisto stands for Compound Astronomical Low-Cost, Low-Frequency Instrument for Spectroscopy and Transportable Observatory. This is a spectrometer on a chip. So basically, we have a box as a backend. Front end you have to design, and analog chain you have to design. And if you just connect to it, you start seeing the sun. Just before I want to see, yeah, this is how the sun looks like as a point object. So x-axis is time, a y-axis is frequency, and this frequency corresponds to height on the solar corona. So if we have very good spectral resolution, we can see very nicely, very thinly spaced heights on the sun. Now I will go back a bit. Yeah. So this is how this is a complete setup for a Callisto network. We have a front end. We usually go for log periodic dipole antenna because it has moderate gain over a wide band of frequency. This works from around 40 to 1 gigahertz. However, we are limiting it to, depending upon RFI and the signal strength, we are limiting it to up to say 500 megahertz or so. This is how we excite the antenna. It's a receiver one. And then this is what the eCallisto backend, the on-chip spectrometer looks like. And then we collect the signal. This is sun as a point observation, as I mentioned, because we are not doing any imaging. So we would not know from which location of the sun these emissions are coming. It's like a combined emission. This is how different radio bursts occur in the dynamic spectra. So for example, type 3s are where electron gyrate along open magnetic field lines, and then type 2s are the signatures of MSD shocks, and type 4s are the one can come from the footprints of the magnetic field lines, or can also come from the core of the CME. This is another example. This all happened before I joined here, sir. You can see a big patch here that is to avoid the FM range. So you see here we are limited at 45 megahertz. However, as we go lower and lower, we can go to till ionospheric cutoff, that is around 10 to 15 depending upon the solar cycle and the activity. So we went ahead and put another antenna last year for the low frequency region below say like 10 megahertz or above that. This is how the beam pattern looks like for it. So it's basically has a wide beam and wide frequency range. This is how the data acquired with this front end and the same back end, the Callisto back end looks like. So you have we have very intense type 3 radio burst, and then again a type 2 radio burst. This we installed it, and then the next day we observed this. It was after this May, when July was also, sun was very active in July as well. And this is a design which is taken from the LWA in US. So it's the front end is not very indigenous. However, we are now modifying these antennas in such a way that it is completely designed by us. Also, you can see at lower frequency below 10 megahertz. So we usually say 15 megahertz is the ionospheric cutoff, but we are also seeing some activities below 15 megahertz. Anyway, so the third instrument which we are building is a spectrograph. It's called wideband solar radio spectrograph. So for that, we are planning to have a 12-meter dish. The front end is not ready yet. The feed is a log periodic dipole antenna. Again, it works from 100 to 700 megahertz. So the size is slightly around 2 to 2.5 meters. The back end is ready, however. So we have a totally steerable dish of 12-meter mesh kind of dish. And then the plan is it will track the sun again as a point source. However, this will have much better sensitivity and detectivity. So this is how the feed would look like. This is how the antenna parameters look like, but I will leave it there. This is how, so this is something called S parameters, which is a parameter to tell us about how good our antenna is transferring the signal to the load, and that is quite good. The VSWR is less than 2 throughout the band. Coming to the instruments I am building at Udaipur Solar Observatory, there are again 2 instruments. One is spectropolarimeter. Till now we were talking about spectrometers, and the second one is an imaging radio interferometer in gigahertz range. So the first one is called ARISO, Advanced Radio Instrumentation for Solar Observations. So the idea is to build a cross-polarized log periodic dipole antenna in a wide band. We are saying 20 to 800 megahertz. The reason behind is most of the solar transients origin correspond to the height range where this frequency falls. And the front end is ready. It just got the news yesterday that it is completely ready and from PRL workshop. Again, just the antenna part is ready, not the analog chain. The back end we are implementing on a board called Radio Frequency System on Chip. It's JetCU216. It's an eval board with ADC and FPGA. And we are planning to have a very good spectral and temporal resolution of 10 millisecond and 10 kilohertz. The only challenge we are facing right now is the data rate and data transfer and data rate. This is how the the design on RFSoC looks like. Okay, I will skip this. So the last instrument, this is the second instrument I am building. It's a radio interferometer. Radio interferometer would see sun as an extended source. That means we will be able to image and we will be able to pinpoint where the radio emission is coming from. And why this is important is, for example, if you have 2 active regions on the sun at the same day, you would need, if you are observing sun as a point source, you cannot pinpoint if it is coming from which active region. If you have an imaging instrument, you can do that. The current landscape nationally and internationally is this. So on x-axis, we have frequency in gigahertz, y-axis time in UT, so it's 0 to 24 UT. You can see in Indian time zone, there is no instrument other than graph at Gauribindu Radio Observatory of IIA, which operates, and also graph operates at just 2 spot frequencies, less than 8, at 53 and 80 megahertz. So this whole Indian time zone from megahertz to gigahertz is empty. So that was the idea behind this project. This is funded by ANRF PM Early Career Research Grant. So the plan is to have 1 meter small dishes, which reflector would work from 1 to 12 gigahertz. And then we will do spot frequency imaging at 1, 4, 8, and 12 gigahertz. These are chosen strategically because we are using frequency multipliers and LOs in such a way that the backend is compatible. We do not have a backend which can work continuously from 1 to 12 gigahertz. That is why we are only doing it at spot frequencies. Also, these frequencies are RFI free at the location. So as it's a radio interferometer, so it has more than 1 antenna. So since it's phase 1, we are planning to have 7 antennas. And then this is how the UV coverage looks like for this instrument. Oh, I forgot to tell the name. It's called Arun SSW. Arun, the name suggests because it represents the sun. It's Advanced Radio Telescope Udaipur Network for Solar and Space Weather Research. The plan, if we have, so at project, I mean, when we were developing this proposal, the plan was to have the longest baseline of 170 meter. However, after working out the number, it appears that that would not be feasible. So we want to demonstrate with the longest baseline of around 50 meters. With this setup, we have a spatial resolution at 1, 9, and 18. We just calculate these numbers. Theoretically is around 2,400, 200 and 134 kilometers respectively. Okay, there is something missing. There should have been one more plot. Anyway, that's fine. I just wanted to show how we were dividing the signals in such a way to tap these 4 frequencies, but that plot is not showing up. So just to summarize everything, at present we have one completely operational radio telescope at USO, which works from, there are like 2 parts, 10 to 80 and 120 to 350 megahertz, which is a sweep-based spectrograph. So the backend is bought. However, the front-end antenna is designed by us. The backend is the Kale spectrometer. It's been fully functional since 2018. And then the second instrument for which the backend is now ready, the front end we are still figuring out because it's a big dish. It works from 100. Then there are 2 instruments which I am building since last year is ARISO. It's Sun as a star observation, and Arun SSW, which we started in August this year. It's an imaging instrument from 1 to 12 gigahertz, and this is a spectropolarimeter. This is a heliograph at high frequency in gigahertz. So radio observations at high frequency, especially from the instrument point of view, already has its challenges. However, we are trying to tackle it. At present, we are planning to have 1 second 50 megahertz spectral and temporal resolution, and this front-end design concept paper is under prep now, and for ARISO, the front-end is ready. We are working on the back-end. So I will leave you to, it's not going next. Okay, fine. I was going to leave you at USO's picture, which I will definitely go to the first slide and show. Go back. Yes. Yeah, so it's a very nice place. I have opening for 2 postdocs. So if you know anyone who is looking for postdocs in instrumentation, I have 1 opening for that. If someone is looking for postdoc opportunity in solar science, I also have 1 opening. These 2 openings are funded by PRL, and there is a very nice fellowship called Vishwas Postdoctoral Fellowship at PRL. So please forward this news. Thank you.
Thanks, Anshu. Yeah, questions.
Hi, nice talk. 2 quick questions. One is like, you were telling that the sun is a magnetic star. So what is a non-magnetic star and how do we classify stars on that?
I mean, or my point was sun is a magnetic star. That means if we have a handle on the magnetism, we can have a handle of the eruptions we are getting it.
Okay.
So in that sense, I was telling you.
Okay, so is there non-magnetic stars as well?
I don't think so.
Okay, cool. The second thing is like you are into instrumentation. So I think usually it's a very underrepresented area in the case of females. So what do you think about that?
That's true, but I can see another instrument person here and another instrument person, Chandra, right? She is an extra person. So in this room itself, we have quite a good. Hirani is there. TMT, yeah. So though there are less people, but it's not about gender. I feel here there are very few people who are working on instrumentation. Okay. So in that it itself is there are like very less people, and then we are itself in that very less number of it. So.
Hi, Anshu. Nice talk. I had a question. You mentioned about this 10 millisecond time resolution. It's a very, very fine
Sorry, what?
time, 10 millisecond time resolution. Yes. It's a very fine time stamp. Yes. So I was wondering about the scientific features that would show up in the sun at that small time
Yes.
stamp, and also wondering about the sensitivity and signal to noise ratio. It's probably very challenging to deal
Yes.
with that.
So I will give you an example of couple of solar radio images which we have made with different instruments. For example, with graph, that's the IA's instrument in Gauribadnu, we have a dynamic range of around 22 dB, and we make images at every 256 millisecond. So, and then say if it is MWA or LOFAR, another two radio instrument, they have a dynamic range of around 60 for sun, 60 dB. So yeah, it's challenging to get it, but we are getting it. One more important point to have high dynamic range is to have quiet sun and active sun seen at the same time. And that is one of the reasons we want to have a very high dynamic range. Coming to the 10 millisecond temporal resolution, we have seen sources on the sun at 3 kilohertz in spectral resolution and 3 millisecond, and our instrument could not go below that. So there are bursts. If you just keep zooming in and zooming in, we start seeing small spikes in these kind of radio bursts which we are seeing. And those are, we usually call it energy fragmentation in solar flares. So if we are able to map those, we can see which part of the... So nano flare based is like defined based on its intensity, nano and pico. But these are not about that. They will still be, say, in micro or so. However, we can see it, if you start zooming in spectra, you can see. So 3 millisecond, 3 kilohertz is the smallest we have seen till now. So that is how these number comes up, which we are, like I am designing right now. Cannot go below 10 because of the data rate. Each day data rates become in terabytes, and then we won't be able to handle at present.
Prajwal.
Yeah, so you showed this type 1 burst versus type 2 burst, where type 1, the variability was at the same time in all frequencies, and in the type 2, it wrote down the frequencies. And so I was wondering, maybe I missed it, but what is the physics behind that? And what does it look like in polarimetry? And has there been simultaneous X-ray measurements of?
So usually all these events in all other wavelengths are cotemporous. So there would be, say, a radio burst, then there would be some signature in X-ray, white light, UV, and all other wavelengths. Coming to all this type 1 to 5, we are very simple solar radiophysicists, are very simple people. How it appeared in the spectra, we just named it 1, 2, 3, 4, 5. So 1 is a signature of flaring active region, 2 is a signature of shock in the corona, and then the frequency depends upon till what height in the sun's atmosphere we can see. And then shape of it also depends upon what is the mechanism which is driving this. So type 3 is when there are like open magnetic field lines. So it goes from very low, it can go from high frequency to a very low frequency. High frequency means close to the sun, low frequency means away from the sun. Then we have this type 2 are like slowly drifting bursts in the sun. So they are shock signature. So their speed cannot be more than, say, 1,000, 2,000 kilometers per second. But for type 3 is because it can go C by 3, C by 6 or so. So that is why it is drifting very fast and goes to a higher frequency coverage.
Yeah, I have a follow-up on that. I was just wondering, so when you showed the video, you had these, flares going off, and they were in the corona. But how low can you go and detect reconnections? Like closer to the sun, etc.
So so 17 gigahertz is around, can vary. So the thing is, this emission can come from different range depending upon the solar activity and density, because they are directly proportional. So this 17 gigahertz is directly proportional to the B field, and lower frequency, say 300 megahertz, is directly proportional to the density. So lower frequency close to the sun, higher frequency away from, ulta. Lower frequency away from the sun, higher frequency close to the sun. Then if you can map each and everything, you can see there are, like, as you go to lower and lower, higher and higher frequency, you can start seeing 2. So that was a bipolar active region. Coming to the reconnection part, we can tell how much energy, / temperature / plasma density or magnetic field at each and every point, limited by our resolution. So that is how we usually tell that this could be a signature of reconnection.
Yeah, but I specifically, like, I was thinking that the detection is always higher up in the corona, right?
No. So we can observe. So we also have, say, 300 gigahertz observation, which is like just at the lowest chromosphere. So we have observations. using ALMA. So this is with Nobiyama, so it's the limit was 17 gigahertz.
One last quick question.
It's about the backend that you're building. I noticed that you have a spot frequency of 12 gigahertz, and you are also, yeah. So and you are using this ZCU. So it has it goes up to 5 gigahertz, right?
So the
5 GSPS basically.
So that is only for the 2 channel. Then we have we have like 4 inputs. For our FS can be 2.5 gigahertz, and that is the image I wanted to show the whole, but that is not here because I think we downloaded it before I added it. So what we are doing is we are doing 1 channel, 1 gigahertz at baseband sampling, and the other 3 we are using local oscillators and then down converting 1 to 12 at 4, 8, and that is why it's like 1 time, 2 time, and 3 times. So 4, 8, and 12 gigahertz, we are using frequency multipliers.
Okay.
And we have LO frequency multipliers, so that is why we are getting that. Yeah.
Okay, thank you so much, Anshu.